Okay, let's get started. Okay, we're going to get started. Ready to start? Okay, ready to start? Okay, so let's review. I'm going to do one from your homework, but before we do that, let's review the idea of finding the rate of change of a composite function. And this rule that we came up with is called the chain rule. Okay, the chain rule is for finding the rate of change of a composite function. So this was really helpful for kind of motivating what this is all about. So our function is g of f of x. Right here. So in the process of finding an output of this function, what comes first? What comes first in the process of finding the output? Just the output, not a rate of change, just the output. What's that? F, right? X goes into F. F gives us some output, and that output then, what? Goes into G, and then G gives us the final output of the function, right? So this process, as if we're thinking about it as a two-step process, it goes X into F, result of F goes into G, and it comes out, okay? So thinking about that for rate of change, we said that if X changes by a little bit, then how much will F change? How much will F change? Yeah.
Change by 5.
So F will go up by 5?
It'll be 5 times the rate of whatever X.
5 times the amount that X changed, right? Because the rate of change is 5. Now, if F changes that much, how much will G change? What's that? 3 times that amount, right? 3 times the amount of the input to G, which is, or the change in F, which is the input to G. So this is the amount of change to the input of G. And so G will change. How many times is that? 3 times that. Remember this? This is how we formed this thing called the chain rule. And so therefore, how much does the function change for a small change in X? How much does it change? Right, 15 times as much as our change in X. So if you think about X going through the function, well now, the rate of change, so if you have a change in X, the rate of change of F is going to be 5 times as much. And then there's a multiplying effect on that change in F in terms of, because of the rate of change of G. So G is going to change 5 times 3 times as much as whatever change in X we have. So the reason I want to go over this is a really helpful way to work on the ones where you had a couple in there where there was it was a composite function but several deep. It wasn't just one function plugged into another. It was like layered like about 3 or 4 times. So if you think about it this way and kind of do the rule backwards, do the chain rule backwards, I think it's a lot easier to understand. So now that we have this in mind, let's check that example in the homework. Any questions on this? Okay, so that question in the homework was this one here. Let me write it larger here. So it's sine. So this notation then means that the whole thing is that sine is raised to the 5th. So I'm going to rewrite it this way. So that's another way to write this function. So now as x changes a little bit, how much does 3x change? So we're saying as x changes a little bit, how much does 3x change? 3 times as much. Okay? And now, as 3x changes, how much does cosine change? Negative sine, 3x times as much. So you see how I'm relating this to the illustration we just did? So I'm working from the inside out here. I'm saying, if x changes a little bit, how much would that change? 3 times as much. And when that goes through that much, so now we've got an amount of change, the 3x goes. How much does cosine of that? How much change do we have there? Negative sine 3x, right? All right, and so now we've got a change of cosine of 3x. How much does sine of that change? Cosine.
Would it be cosine of cosine?
Yeah, cosine of 3x. And now when we have that change of that there, how much does that thing to the fifth change? 5 times. Yeah, so it's going to be the power rule with respect to the input. This is the input, right? Sine.
Cosine 3x.
So on these to the, and that's it. So I think the way that the conventional chain rule has you go the other way. It has you start here, and then develop it this way. But I think this is kind of easier to keep track of if you just think of in terms of when x changes a little bit, how much does 3x change? Well, it changes 3 times as much. And then now when 3x has that amount of change, how much does cosine 3x change? Well, negative sine times, or negative sine of 3x times as much. And so then we have an amount of change for that input. How much does sine of that input change? Well, it changes by cosine of that input, and then everything in the brackets, you have an amount of change, right? How much does it change? Well, the power rule tells us 5 times that input to the 4th times as much. So it's when you're going the other way, sometimes I think it gets confusing. Maybe this is helpful. Any questions on that? Yeah, Ryan.
I think, I'm not sure if it was this one or a different one in the homework. I got marked off wrong because I didn't take that 4 and put it back in next to the sign towards the end there.
This one?
Yeah.
It's the only 4 I see.
Because my answer, I don't remember exactly what question it was, but my answer was almost identical to the one that the homework had asked, except it put the exponent back next to the sign function.
So we'd have to look at it. I have no idea. We'd have to look at it closely.
Because it's signed to the 4th, so you have to put it by the end over, like, instead of, that's what he's saying.
So was yours originally something raised to the 4th?
It was it was like sign of something with
Right. Well, this is to the 5th. Oh, yeah. So mine is sine 5. So the power rule says that you multiply by 5.
And I did that, but when I put the answer in, it marked it wrong because I didn't take that 4 and put it back next to the sign.
Yeah. So I'd have to look at it.
I think he's saying the exponent was just back.
Like, you see how it's written in the original
5 sine to the 4th times to that x, that cosine 3x.
Oh, so it didn't let you do this. You had to put the 4 here.
I'll show it to you after class.
Well, then you might have had parentheses wrong. This should be correct. You should be able to write it this way and get it correct. Because it should recognize other forms of the same.
I'll have you look at it.
I don't want to get too bogged down in algebra, Janae.
So, I have a question. Do you want us to leave it in that whole form, or do you want us to, like, simplify it so that it just being...
It doesn't matter. It doesn't matter. Right. So it's this. Yeah. So we can multiply the 3. We get negative 15. Yeah. Doesn't matter. So now, what we've got coming up next Thursday is your first attempt at what's called the mastery exam. Mastery exam is purely knowing how to follow these rules and find the closed form rate of change functions. So I'm going to post a long list today. This afternoon, I'm going to post a long list. And actually, all your problems on your mastery will come from that list. Okay? So you're going to you'll be able to work on all the ones in advance. Okay? So when you do that mastery exam, don't do it. So that you're just, if you start simplifying, then you're risking that you're going to get it incorrect. So just do the first step like this and leave it. Just do the first step and leave it.
Is there a grade on the mastery exam calculated into our grade?
Oh yeah, definitely. And to pass it on the first attempt, you have to get 90% or better. And if you get 90% or better, you get 100. Okay? If you don't get 90%, you're taking it a second time for a lower grade. Okay? So just get it, pass it the first time. You get 100%. Okay? And it's worth half of a normal exam. It's worth half as much. 100%. So you got, but this is mastery, right? So by mastery, we mean you have to have it. So that's why the standard is so high, 90%.
I thought on the syllabus it said 85. Did that change?
Yes, it changed. Sorry. 90. Other questions? And that's, sorry, from previous semester.
Is there extra credit that we're doing?
The extra credit is getting 100 on the mastery exam.
So if we get the 100, do we get like an extra?
I'll consider it for everyone else, Kevin,
Alright.
but not for you.
Is there,
Yeah.
is it possible to go back into this homework and do similar exercises? Or
Not right now, like in class?
No.
Yeah, you
For
should-
our own study,
yes.
so we can make sure we do it.
So what I have to do is I have to pass, what I'll do is I'll post copies of those sets and they'll all start with an R for review. So you'll see duplicate sets of all these and they'll say R. And the due date will be like at the end of the semester, so they won't be for any points, but you'll go in and be able to
Go through and work.
practice. And it'll have a limited attempts.
That'd be awesome.
Yeah, so I'll do that this weekend. Okay, other questions? All right, so we've got some more rules to do. Okay, so what we haven't dealt with yet is products and quotients. So consider these two functions. And what about, let's talk about the sum, right? So if we wanted to take the derivative or the rate of change function of the sum of two functions, we developed the rule for that, and what is the rule for that? It was exactly what we wanted and hoped for, and everything was happy, right? What is it? So we got the sum of functions, and we want to find the rate of change of the sum of functions.
Just the estimated change of each individual function plus one.
So he's just going to take the rate of change of f and add it to the rate of change of g, right? Yeah. So it's like we haven't even. It's so natural now we don't even think about it. Okay. So what about? Then what is the rate of change of h if h is the quotient, say, of the two functions? What's the rate of change of h? Was it?
Oh, well, I know it's it's g of x. It's slowly how next time you do it.
No, it's the rate of change of f divided by the rate of change of g, right? And then the rate of change of the product is the rate of change of the first times the rate of change of the second, right? Wouldn't it be nice, right? Wouldn't it be nice? No, that's not it. Okay, so we got our wish with sum and difference, right? But it's not so easy with, if you have a quotient of two functions, it's not the quotient of the derivatives. Thousands of calculus students through the ages have tried to make it the quotient of the two rate of changes. It's not. Similarly with the product. And what happens is we learn what the rule is, but then we get into a more complicated problem with context and lots of things going on, and we get to a derivative and it's a product and we forget. And then we try to do this. So that's the common That's the common thing that happens. So it's in a larger context. That's where we really have to be careful. When we take the derivative, when we find the rate of change, we have to know the rules well enough and apply them correctly. Did you have a comment?
Yeah. When we're doing like derivatives and like chain rule, I know like my old professors would say like just do pandas, like start with parentheses and like or like the power rule and like work your way down. But when you just did the chain rule for the middle one, you worked from the inside out.
Mm-hmm.
What's your
Well, we're getting to the complicated ones. We're getting there. Yeah. We're going to talk about when things get complicated and we have many rules involved at once. What's a good strategy?
Okay.
And we're talking about that today. Okay, but first we got to get so we're going to start with the product rule first. So the closed form rate of change for the product of functions. How are we going to start? We want a closed form rule for finding the rate of change of the product of functions. Can you write the first step? You should be able to. Want to find the rate of change of the product of two functions. And so I've told you ahead of time, it's not the product of the rate of changes. It's not the rate of change of f times the rate of change of g. So how do we get started? What's that? Yeah, but so we're pretending we've never had calculus before, and we got to come up with this. Alexander.
The open form.
So can you tell me what the open form would be?
Fx plus h, gx plus h.
Okay.
Minus fx times gx
Uh-huh.
plus h.
All right. Here we said. Yeah. Open form. Start with the open form. It's our trusted form. We know that that's the rate of change function, given a whatever our starting function is. Okay. So remember, when the other ones, when we had combinations of functions, whether it was the sum of functions or difference of functions, we looked for a way to get, for instance, so what is the rate of change of f in open form? What is the rate of change of f in open form?
Times x plus h.
Ryan?
F times x plus h minus f of x over h. Isn't that open form?
Well, not times. F of, right? Yeah, f of. Yeah, that's not complicated. Okay.
F of x all over h.
Okay. So we notice we've got f of x plus h here, but it's multiplied by this g of x plus h. So what might we kind of insert here so that we might be able to move towards something that looks like that, strictly the rate of change of f. So what term could we were just thinking about, maybe we wanted to move towards getting the rate of change of f. What term could we insert in there? Any ideas?
Could you subtract it?
Yeah, we're going to add or subtract the term. What do you want to subtract?
So just add or subtract the g of x plus h.
Okay, but then would that give us this then? All right, so he's got a good idea. Subtract g of x plus h, but we need it to be f of x plus h minus f of x. So what else could we put with that term?
So minus f of x.
So the whole term would be what? So imagine that we're gonna factor out g of x plus h, and it's gonna leave us this. Anybody? Can anybody see it? It's kind of hard to see if you're not algebra. Anybody? Okay, so what if we had this? What if we had f of x times g of x plus h? Then what could we do to those two terms to get something like this?
Use this to what f of x times g of x plus h.
We're going to insert it. We're trying to come up and create and get this. So we're going to alter the form of this. We're going to insert. We're adding it in ourselves in order, in the end, to get something that looks like that.
Are we doing it like magically, or like we're doing like
Yeah, like.
No, like,
Do you have to do that, you have to do that
Like,
on
are we
both
gonna
sides of
multiply
the,
that?
Yeah, so right, you can't just subtract something.
Yeah.
It will change the value of it.
so you're gonna do it for both.
So then if we subtracted it, then we would have to
Get to the bottom?
add it, and then it would be like adding 0, right?
Yeah.
So if we subtract that and add that, so you know, you wouldn't know to do this, but I was just trying to kind of lead you to see if you could see it, okay? But why do we do this? Because it works. Why do we do this? Because it works. Because now we kind of see that we've got our rate of change of f forming. If we did what to those first two terms? If we did what to those first two terms? We'd have the rate of change of f. If we did what?
Factor it out.
Factor out
The g of x plus h.
g of x plus h.
That makes sense.
Okay, so but if we're going to subtract it, we got to add it to keep the value the same. But then look what happens here. Do you notice what just happened? So now if we group this thing that we added with this, what do you see?
The f of x's get factored
Do you
out.
factor out the f of x's?
And it leaves a g.
Leaves a rate of change of g. Do you see that? So wow, does it work, right? Not only did it get what we wanted for f, but this thing what we added to keep the value the same gives us the rate of change of g.
That's pretty good.
I agree. It's pretty tight. So we're gonna factor out the g of x plus h of the first two, and we're gonna factor out the f of x of the second two, and that leaves now we're starting to see the rate of change of f and the rate of change of g starting to form here. So, did you catch it? So we subtracted and added, then we grouped these two together, and then we grouped these two together, and by factoring out, we're really close here to the rate of change of f in the first and the rate of change of g in the second. And so we're just splitting it apart, right? Common denominator of h, split apart those into two, common denominator of h. And so what is the rate of change of the product? So as h gets very small, what is g of x plus h? As h gets g of x, right? And then what is this as h gets very, very small? The rate of change of f. And that doesn't care what h does, it's just the function f. And then what happens here as h gets very, very small? Rate of change of g. So we get one function times the rate of change of the other plus now our other function times the rate of change of, in this case, g.
Was this is this how the product rule is actually initially like created?
You were there. Yes. Okay, so there's a nice symmetry to this rule that makes it easy to remember. You've got two functions, so you're going to take one function as it is, times the rate of change of the other, and then you're going to switch it and add them together. So you really can't miss because multiplication is, you can change the order of multiplication and you can change the order of addition. So all you got to remember is take the one function as it is, times the rate of the other, switch it, and add. Okay? So we could say this as the rate of change of the product is the first times the rate of the change of the second, plus the second times the rate of change of the first. So all you got to do is remember the symmetry of it, and then it's pretty hard to miss. Okay, it's pretty hard to miss. So that's the product rule.
I have a question.
Sure.
Like, is there any way you can go like 2 slides back really quick? Or I could just explain it to you.
Okay, go ahead.
Where is it like, because it said g of x plus h, and then it said like the form of the original function.
Yep.
The x plus h, that becomes g of x because h goes to 0, right? That's why.
Yeah. What happens to that as h gets really small?
Okay.
As h gets really small, g of x.
Okay.
Okay, so here's an example. And what we're going to do now is these things get complicated. Is the first question we're always going to ask is, what's the structure? What's the overall structure or the big picture of this function? So, what is it? Is it something to a power? Is it a quotient? Is it a composite function? Is it a product? The big picture of this is the product of two things, right? The big picture of function f is the product of two things. Okay, and so we'll call them G and H. Okay? We'll call them G and H. And so the big picture will then govern the big picture of how we take the rate of change. What's the overall, so what rule are we going to use if the overall structure is a product? We're going to use the product rule. Okay? Okay, so here's just a comment. So remember that we can use these interchangeably. Sometimes in different situations, one's more convenient than another. Okay? Now, we have to also keep in mind, what about this notation here? If we're using them interchangeably, then what do we...
That's an approximation.
Okay, but if we use them interchangeably, then how can we say that they're equal?
You're gonna add a limit to it.
That has
Or,
to
not, but that equals limit of the open form.
Right. Or we can just consider what?
Exactly.
H is very small. Just if we just say we can use this and say H is very small, and then they're interchangeable. So just always remember that's the approximate rate function that's based on the average rate of change. But we can use them interchangeably as long as H is small. For that first one. Okay, so we've got the overall structure, and so then our plan is use the product rule. Use the product rule. The first times the derivative of the second, plus the second times the derivative of the first. All right, so let's what is the derivative of g? 8x cubed. And what's the derivative of h?
H, it's 6x.
Just 6x. So that now we apply the plan. Okay? G times the rate of change of h plus h times the rate of change of g. Make sense? Any questions? Okay, so what about quotient? So quotient, instead of starting with the open form, we can use what we just learned. Okay, so the open form maybe gets a little too hairy for us to take the time for. So let's use what we just learned. So how can we use what we just did to apply it to f divided by g? Yeah.
Would it be f divided by 2 times plus f prime divided
Okay, so you're kind of following the same form. So we still want to derive it. We still want to derive it, but yeah, Ross. Okay, f of x times 1 over g of x. So then we're turning that quotient to a product, and then we can apply the product rule. Or we could say f times what?
G of x to negative 1.
Yeah, g to the negative 1. Okay, so if we do f times g to the negative 1, we can apply the product rule to derive what the quotient rule will be. So you write the first step. So we're practicing. So the overall structure of this is it something to a power, or is it a product? Product. Right, so because it's this times this. All right, so let's just apply the product rule here. The product rule says the first times the derivative of the second plus the second times the derivative of the first. So the first times the derivative of the second plus the second times the derivative of the first. So the question is, what's the derivative of the second? So that's really all we can do right now is, what is the derivative of the second? What's the structure of that? So what rule will we apply to do the derivative of the second? Is it a product? Alexander?
It's just negative 2 of x to the negative second.
Say it again.
Negative g of x to the negative second.
Negative g of x to the negative second power. What do you think? Agree? What rule did he apply there? Power rule, because that's the structure of that little part right there. The structure of that is something to a power. So you apply the power rule. Is that what you're going to say, Kevin? Yeah. So we get f times, well, we forgot though, right? But that's actually a composite function, so that the overall big picture was power rule, but it was a composite function, right? So if we need by the chain rule, then we need the rate of change of g also, like what you did for your homework. See that? Why? Because it's a composite function. It's g raised to the negative 1, not just x raised to the negative 1. There's a composite function. So what happens first? A little change in x. How much does g change? The rate of change of g, right? And then how much? Now I've got that change in g. How much does that change? Right? So it's a composite function. Okay, so this is, we're not going to take time. This is just algebra. We're just changing the form of this, okay? So if you just want to go from this step, this is all we want to, just take it from this step to the answer, okay? So we don't want to, okay? And so this is what we call our quotient rule. This one's harder to remember because it doesn't have this nice, easy symmetry that the product rule does. But we've got a trick, okay? So this is it. So what are we saying? We're saying it's the denominator times the rate of change of the numerator minus the numerator times the rate of change of the denominator divided by the denominator squared. Which is just a couple steps of algebra from this right here, using the product rule. Okay, so now the order is important, right? With minus, you gotta get the order right. Okay, you can't switch it like you can plus. You gotta get the order right with minus. Okay. So here's using the R notation, here's using the prime notation. Okay? But they're interchangeable here as long as h is sufficiently small.
Are we going to do the proofs on the master exam?
Not on the master exam, but third exam, deriving things from open form is fair game for sure. But the master exam is just using the rules. It's just using the rules.
Is the master exam multiple choice?
No,
Free response.
it's free. You have to write them out perfectly. So here's, you don't have to copy all of them, okay? So just copy your one or two or your favorites, but they all say the same thing. And here's kind of a trick to do this. Okay? So thinking of the denominator, just nicknaming it low, because it's down here, and then nicknaming the numerator high, there's this, little chant. You can do a little chant. Low d high minus high d low over low squared. And it's off to where we go. Okay? So low is our nickname for the denominator, high is our nickname for the numerator, and so this little chant can help you remember it. And you gotta get it right, because minus is,
Do you want a more musically inclined chant?
Okay, maybe they do. Sure.
Low D high minus high D low, draw a line and square below.
Draw the line. I've never heard that before.
No.
Low D high minus high D low, draw the line and
Square below.
square below. Okay? And so really to remember, that's great. To remember that, all you need to remember is this first part. If you can just remember low, D, high, then the rest falls into place. Okay? Whether, so using the either chant. But really just, if you can just remember low, D, high, that's how it starts. Then the rest, you can get the rest. Questions on that? So what are we doing? So we did the rate of change of the product of functions. Now this is the rate of change of the quotient of functions. Okay, so back to our original example when we said this. So what about if h is the quotient of sine and e to the x? What is the rate of change of h? What is the rate of change of h? See if you can do it. So you're going to apply that rule. Low d high minus high d low over low squared. Or draw the line and square below. Yeah. You want to do it?
Yeah.
Tell me.
G times R of F plus F times R of G over G squared.
G times the rate of change of f with respect to x. Keep going.
Plus F of X. Okay, it's minus.
Minus.
Minus
Okay.
F of X R of G.
So what is R of G? Can you say out what it really means?
The rate of change of G
With?
with respect to X
Good. Okay.
over G squared.
Yeah, practice that. So every time you see that notation, practice the rate of change of f with respect to x. Okay? All right, so what is g of x? Someone want to take over? Yeah, Molly. E to the x squared?
Oh, yes. No, sorry, can I just say the whole thing?
Yeah.
Wait. Never mind, sorry.
So we just go one thing at a time now. Now we got the whole structure of the rate of change.
It's e to the x
E to the x
times cosine x
times cosine x
minus sine x
sine x
times e to the x
e to the x
all over e to the x squared.
e to the x squared. Okay, and so just getting in this habit of not doing any simplifying, we're just going to stop. For the mastery exam, this is what you want to do. If you go further, you're risking making an error, and it makes it incredibly hard for me to grade. So just do the first step and stop. Okay?
Wait, yes. It's time.
You good?
Yeah.
Yep. Okay, what about the product? So that's the rate of change, that's the quotient. That's what we said, right? Okay, so now, quickly, product. So what is the product rule? And what would, if k is the product of those two functions, what would the rate of change of k with respect to x be? Who wants to give that a try? Jamal, want to try that?
Ex cosine x minus plus sine.
How about, can you tell me just in terms of f and g, first of all? That's okay.
The derivative of f of x times g of x plus or g of x times x.
Okay. So I think you said the derivative of f. What'd you say?
Times g of x plus the derivative of g of x times f of x.
Okay. How about the fact that he didn't do first times the derivative of the second plus second times the derivative of the first?
It's product.
Is it okay, or do we need to do it?
To me, it's addition, so it's going to be the same thing.
Yeah. So multiplication is interchangeable or commutative, and so is addition. So what he's done is fine. There's like 8 ways to write it or something. What's it, 2 or 6? Yeah, 8. There's 8 ways. There's 8 different orders you could write this in, and they're all correct. It's the overall structure that you have to remember. rate of change of one times the other, plus, switch it. So we get sine x e to the x plus cosine x e to the x. Any questions so far before we start doing some hard ones? Okay, so I'm gonna let you go to work here. Oh, this, hey, you guys, you're gonna like these eventually. You're gonna like one like this.
Is that because they're gonna get harder?
Right, exactly. Gilbert's okay, so listen, hold on a second. So, what's the first question we always ask? Big picture. What's the overall structure? Okay, what's the big picture of it? The big picture of the overall structure is going to then indicate which rule you're going to use in the big picture. Okay, but then within that rule, you're going to use other rules. Okay. So why don't you give this a shot? So make sure you know what the big picture is first. That's going to govern the structure of the rate of change. And then within that, you will have other rules to apply. So we haven't really done one like this, but I'm just going to let you loose and see how you do, and then we'll come back and talk about it. So copy that down. Yeah. Overall structure. Shannon.
The geostacks times the R of f of x, the rate of f of x, f of x, the rate of g of x over g of x squared.
Right, and which rule is that? That's right. Quotient rule. The overall structure is a quotient, so the overall structure of our rate of change will be quotient rule. Okay, so we pinpoint what our high and our low is. High is we're going to call F, or I'm going to call F. Low we're going to call G. And so then the rate of change is going to be low d high minus high d low. Draw the line, square below. Okay, so what we're going to need the rate of change of F. How do we do the rate of change of F? It's chain rule, right? It's a composite function. So within the quotient rule, we have the chain rule. Because in the quotient rule, when we get to the rate of change of F, the rate of change of F is going to be applying rate of change to a composite function. So we need the chain rule for that part of the quotient rule. Similarly, your denominator G is another composite function. So you have to apply the chain rule for both of those.
Okay, so we do the chain rule before we start doing the other.
This is just to get organized. So this is the overall structure of our rate of change function.
I got that.
But within it, you have these. So it's just helpful. It's helpful. Let's get those pieces of this.
Okay.
And then we can put them where they need to be. It's not required. If you can do it all.
No, I think this is actually.
Yeah, this is really helpful. It's really helpful.
Because I was doing everything first, and then I'm trying to figure out how am I going to do the chain rule after I get this thing this long.
So is this a more helpful strategy?
Yeah, that's a lot better.
Yep. So again, here's the structure of our rate of change function. So let's get the pieces, and then we'll just plug them into the structure. Okay. So we're ready to do it. So it's low d high minus high d low, low squared. We're not going to go any further. Just do it like that.
Can you go over the chain rule for G then?
Okay. So what's the overall structure of G? So now we're just going to do the rate of change of G. What's the overall structure of that?
Well,
E to the something. It's E to the something. So
Right.
it's
E to the
E.
X.
And what's the rate of change of E to the something?
each is something.
It's just the E to the something. But then it'll be also times the derivative of the interior function by the chain rule,
C.
like you did for homework last night.
Right.
So it's going to be, so this is kind of flipped. So this is the rate of change of E to the something is E to the something times The derivative in the interior part. That's your chain rule. Not clicking?
Not yet.
Okay.
Not yet.
Yeah, Chris.
Could we have made it a product rule?
Yeah, you could have. You could have. But the idea with here, the idea of this one was to practice the quotient rule. But yes, you could make it a product. Okay, questions on that? Can we do one more example? So again, overall structure, get the pieces, apply the structure. Okay? Overall structure, get all your pieces, apply the structure. All right, so we've got all these different rules. This is what the mastery is about. We've got all these rules. Okay? We got to practice, we got to remember them, and we got to use them together. That's the whole point. That's the point of the mastery exam, is to do this. We're going to skip this. So this is, let me just talk, we're going to skip it, and I'm going to get to another example. But here, so to find a closed form rule for tangent x, we could go by open form, or we could use the quotient rule on its definition of sine over cosine. Don't write this down. So we're going to use the quotient rule using sine and cosine to derive a closed form for tangent. When you use identities, you get secant squared. Okay? Secant squared. So the rate of change of tangent x is secant squared, which can come from using the quotient rule on sine divided by cosine. Okay. Go. Just write out a plan, all right? We're not going to be able to get the whole thing, but see how much of a plan you can get here. Yeah, so instead of writing, let's just talk to your partner about a game plan. This is very long and complicated. So what's a game plan? Just talk to the person next to you. What's a roadmap? Roadmap for
I would, yeah, just
Okay, overall structure. Overall structure of q to the x, or qx. Quick, let's get out of here. What's overall structure? Quotient. Okay, so that'll be f, we'll call this, will be our numerator, and k, denominator. You can use something else, use f and g, okay? So the plan is quotient rule. What about the rate of change of f within the quotient rule? Product rule. What about the rate of change of k? Pretty easy, right? Okay. So f we're going to see as the quotient of, or the product of g and h. So within the quotient rule for the rate of change of the numerator, we have the product rule. And we're going to find that product rule and we're going to put it back in where? Here. So find that product rule for F, and then insert it back into the structure for the quotient rule. So there's our product rule for F. There's our quotient, or rate of change of the denominator, K. And so then there it is. Okay. Any questions?
Would it be easier to factor out the top and then just use power rule on them? Or-
You multiply out, and
Yeah,
then just as a polynomial?
yeah.
Maybe, but so again, you can do algebra and end up applying different rules. We're just practicing this idea of rules within rules. Okay. I'll have stuff up for you this afternoon for the weekend and to get ready for Mastery Attempt 1. Thursday. Thursday.
I